What if I told you that 5,000 meters beneath the ocean's surface, in a place so dark, so cold, and so crushing that no human could survive even seconds, an AI-powered drone captured something that shouldn't exist? Down there, beyond sunlight, beyond satellites, beyond easy reach, scientists sent a fully autonomous AI drone into the abyss. Its mission was simple: map the ocean floor. But what it recorded was anything but ordinary. At first, it looked like nothing more than a small rock, about the size of a potato, harmless, unremarkable. But as the drone's sensors scanned it, the data began to shock the research team. This wasn't just rock. It was packed with some of the rarest and most valuable metals on Earth, materials critical for advanced technology, clean energy systems, and next-generation AI. And that's not even the unbelievable part. At depths where pressure can crush steel and temperatures hover near freezing, something about this discovery appeared to defy what we thought was possible. Early estimates suggest its value could exceed $3 trillion. Governments are watching closely. Private investors are moving quietly. And the scientists involved are being unusually careful with their words, because what the drone recorded down there may not just change the global economy, it could change what we believe about our planet, and possibly life itself. Before we go deeper, hit like and subscribe, because what we're about to reveal is something they don't want everyone to see. The journey into the ocean's basement. The Clarion-Clipperton Zone, or CCZ, is one of the last remaining uncharted territories on Earth. Located far out in the Pacific Ocean, between the warm beaches of Hawaii and the coast of Mexico, it covers 4.5 million square kilometers of seafloor. This enormous abyssal plain is bigger than the entire European Union. Depths descend to 5,500 meters, where temperatures are barely above freezing. No sunlight has ever reached, and the pressure is 500 times greater than at the surface. We cannot get much closer to visiting another planet while still being on Earth. Mining-related companies had been mostly interested in this puzzling area for decades due to the treasures strewn across its floor: nodules of copper, nickel, cobalt, and manganese that could be worth billions of dollars. However, a group of scientists from the Scottish Association for Marine Science, under the direction of Dr. Andrew Sweetman, deployed in 2021 with a completely different objective. They were pursuing something considerably more essential to life than riches: understanding how oxygen cycles through the deep-sea mud, where some of the most bizarre living forms on Earth managed to survive against all the odds. The research team employed remarkable devices known as landers, AI-guided robotic laboratories that sink to the bottom autonomously and carry out precision tests without the need for human assistance to reveal these mysteries. These intelligent landers carried benthic chambers, which are sealed receptacles holding samples of mud and seawater, along with high-precision oxygen sensors. The idea was straightforward. Scientists could determine the biological activity in these deep sediments by analyzing the real-time data the AI drones transmitted back, measuring the rate at which oxygen was consumed by mud microorganisms. The ocean, however, had other ideas. From the very first readings the AI drones sent back, the data reported something completely nonsensical. Instead of a steady decrease in oxygen levels as the microorganisms consumed it, the sensors detected an increase in oxygen within the chambers. The scientists initially assumed it had to be an error. "You learn to distrust your instruments when you're working at these depths," one researcher noted. "Salt water has a way of fouling even the best-designed equipment. The tremendous pressure can distort metal, and the cold can impact electronics. So they examined everything. They recalibrated the sensors. They conducted the trials again. They dispatched fresh AI drones to several different areas. And yet, despite their efforts, the impossible data kept coming through. Oxygen levels were rising when they should have been falling. The crew had to come to the shocking realization that in total darkness on the ocean floor, something was going against the laws of nature. After 5 years of meticulous testing across multiple expeditions, this finding upended everything. Since plants and algae use sunlight to separate water molecules, we have always understood photosynthesis to be the source of breathable air. This discovery, in a sunless abyss recorded by autonomous machines, was therefore analogous to finding fire underwater. Radical explanations had to be considered. Could certain minerals be releasing oxygen through a reaction with seawater? Was there an unidentified chemical reaction occurring? Or could there be an entirely new kind of process producing it in ways we did not yet understand? The consequences extended far beyond scholarly interest. The fact that oxygen could develop in the absence of sunlight and living organisms called into question our fundamental understanding of how deep-sea ecosystems work. It might help explain how life survived in Earth's early history, when the atmosphere was deficient in oxygen. It might even raise the prospect of discovering life on ocean worlds like Europa or Enceladus, where sunlight never penetrates, yet life-sustaining chemical processes could exist, eliminating the biological suspects. The first suspect in the strange oxygen readings was life itself, specifically microbial life. Despite its harshness and remoteness, the deep sea is far from dead. Microbes have been found in some of the most extreme places on the planet, including deep underground, inside Arctic ice, and even close to boiling hydrothermal vents. Many of these microbes can live without oxygen or sunshine, depending instead on sulfur, methane, or iron-based chemical processes. So when the AI drones detected rising oxygen levels in enclosed chambers deep beneath the CCZ, bacteria were the obvious suspect. To test this, the researchers set out to eradicate all life within the chambers. They applied biocides, substances made specifically to sterilize environments, to the benthic chambers. By rupturing cell membranes and interfering with metabolism, these substances are known to neutralize microorganisms entirely. The sterilized chambers were once more lowered to the ocean floor via AI drone, roughly 5,000 meters below the surface. The sensors settled into the sediment and began transmitting data. Everyone aboard the research vessel anticipated that oxygen levels would either remain constant or gradually decrease. They did not. When the data feeds came back, the findings were astonishing. The oxygen content of the sterile, enclosed rooms increased, just as before, not abruptly, but unquestionably and steadily. The pattern was unmistakable. Despite the removal of all microbial suspects from the equation, the odd trend the AI drones kept recording continued. This was no longer merely a strange readout or a malfunctioning instrument. The observation was now routine, supported by strict control procedures and reproduced in carefully monitored settings, yet it did not conform to any known science. The scientists intensified their efforts. They repeated the sterilization using multiple techniques and dosages. They shifted chamber placements and sizes across different CCZ regions to eliminate local influences. However, the outcome remained the same. Regardless of what they attempted, oxygen was appearing where it should not, and the drones dutifully kept recording it. An electrical clue. In 2022, while attending a deep-sea mining presentation, Dr. Sweetman heard something that stopped him cold. A speaker casually referred to something discovered on the ocean floor as batteries in a rock. It was a throwaway phrase used to explain complex mineral behavior, but it sparked an idea. His team had been gathering enigmatic data transmitted by the AI drones from the CCZ for over a year, and while most scientists had previously regarded the metallic nodules as inert lumps, Sweetman began to wonder, what if they were active? The team was already aware that the interaction of seawater with certain minerals can produce tiny electrical currents. When they tested their specimens under simulated conditions, the results were startling. Under specific circumstances, the nodules showed signs of small but measurable electrical currents. This was not merely fascinating, it completely altered the way these deep-sea components were perceived. They were not just passive metal deposits, they might be active participants in their surroundings. Later, aboard the research vessel, floating hundreds of kilometers from any shoreline, something further unexpected was captured. While the AI drones conducted routine diagnostics, onboard equipment detected an anomaly, a low-level, steady electric signal of approximately 1 volt. It may not seem like much. Compared to the electricity required to light a lamp, it is far less. But for scientists working in a zone where chemistry, pressure, and temperature are known to be stable and predictable, 1 volt appearing from nowhere demanded an explanation. No electrical sources were present in the area. No organisms were large enough to produce such a charge. There was no movement, no heat. Yet the current persisted, and multiple instrument checks confirmed it was no error. Something deep in the shadows was steadily driving electrons in one direction. It was silent, slow, and invisible, unless you had an AI drone specifically designed to look for it. The implications were profound. Even a small electric current, under the right circumstances, can stimulate significant chemical processes. That is electrochemistry at its most fundamental. With sufficient time, even low voltages can meaningfully alter a solution's molecular composition. It is how seawater causes metal to corrode. It is how hydrothermal vents produce the substances that support life. And it is the invisible means by which energy moves across seemingly inert regions. The secret of the breathing stones. After years of painstaking investigation, with data continuously fed back by AI-powered autonomous drones, Dr. Sweetman's team arrived at a remarkable conclusion. The answer to the mystery lay in the very objects that mining companies had long coveted, the polymetallic nodules scattered across the CCZ floor. These potato-sized lumps, rich in manganese, nickel, cobalt, and copper, were functioning as nature's deep-sea batteries. When the nodules come into contact with salt water under the immense pressure of the deep ocean, their distinct metal composition generates microscopic electrical currents. These currents are just powerful enough to split water molecules into their constituent parts through a process called electrolysis, the same fundamental chemistry employed by industrial facilities to produce oxygen and hydrogen. The oxygen slowly bubbles into the surrounding environment, while the hydrogen dissipates into the water. This dark oxygen synthesis represents a completely new category of natural oxygen production. It is entirely geochemical, a trick of chemistry and physics playing out in nature's high-pressure laboratory. Unlike the biological processes science has understood for centuries, this process requires no sunlight, no plants, and no living organisms of any kind. None of it would have been discovered without the patient, tireless recordings of the AI drones sent into the abyss. Dr. Sweetman remarked, "This isn't just about scientific curiosity. We have discovered a fundamental Earth function that was hidden in plain sight. We must now understand it before we can consider interfering with it." History rewritten. The discovery of dark oxygen, captured in meticulous detail by AI-guided deep-sea drones, has upended the fundamentals of ocean research. The production of oxygen, which is necessary for the vast majority of life on Earth, may now be achieved without sunlight, without photosynthesis, and without living organisms. If oxygen can form through geochemical means in the darkest, most extreme environments on our planet, what else might be possible elsewhere? Worlds previously believed to be inhospitable to life, Mars, Europa, Enceladus, may prove more livable than science had supposed. Where comparable metal-rich seafloors exist beneath liquid oceans, far from any star, similar processes could be silently generating oxygen in the dark. For astronomers, astrobiologists, and geochemists, this changes the calculus of what conditions are necessary to sustain life. Yet the same nodules responsible for this extraordinary process are also at the center of the rapidly expanding deep-sea mining industry. Companies are actively developing plans to harvest these ancient rocks for their metals, which are essential components in renewable energy infrastructure and electric vehicle batteries. This creates a profound dilemma. Could the removal of these nodules inadvertently destroy a natural oxygen source we barely understand? Could entire ecosystems that depend on it be wiped out before we even find them? What began as a mission to monitor the oxygen content of deep-sea sediment, carried out by AI drones, venturing where humans cannot, has evolved into a race against time. Scientists are now under pressure to understand this hidden system before it is permanently altered. Once considered a lifeless desert, the deep sea is proving to be far more vibrant, dynamic, and enigmatic than anyone anticipated. 5,000 meters below the surface, under the silence and crushing pressure of the ocean's abyss, these breathing stones have been quietly sustaining the deep for millions of years. It took an AI drone to finally record the truth. What comes next is entirely up to us.